Okay, so in the last video we took a look at how to extend Newton's second law for the case where the accelerated coordinate system was undergoing a translational acceleration with respect to the inertial frame. Now I want to go and take a look at rotating systems, and then we'll eventually put it all together. So, rotating coordinate systems. Okay, so following our convention as before, we'll make the black inertial and the red rotated, or red accelerated, which in this case will be a rotation. So this is my z-axis, x, y, in the inertial frame, and we can identify actually let me redraw that just to need a different thickness here. There we go. Whoa. How is that worse? Oh, there we go. So x, y, z, like so. We'll have the unit vectors I hat, j hat, and k hat. I would strongly urge you not to use dots when writing I hat and j hat because we're going to be differentiating them real quickly, and you don't want to have the dots for differentiation messing up the dots for the letters themselves. Okay, so then we can imagine out here some point P. And that would be our vector r. Okay, we can go ahead and repeat this whole exercise for some arbitrary rotating frames. So bear with me here. So this is my x prime axis. Say this is my y prime axis, and that's my z prime axis, like so. So then the unit vectors would be, there's my I prime hat, my j prime hat, or my j hat prime, and then there's my k hat prime, like so. Again, we would be looking at some point, at that same point r, and we would say that it is located at r prime, like so. We also need to keep track of how it's rotating. So let's say this is our axis of rotation, and it's rotating around like so. In that case, omega will point along like that, so that's our rotation vector. And we can also go ahead and construct a unit vector for that, like so. We'll call that n hat. Okay, so with all of that, when both observers are looking at this same point P here, they're going to agree on where it's located. Coordinate systems are an invention of man, not of nature. So they will agree that r equals r prime. Actually, let's do the r prime in red just to help keep it straight. There will be absolutely no disagreement about it. Now, they will disagree in how they represent it, but they will agree that the vectors are the same. So the unprimed observer will write it as x I hat plus y j hat plus z k hat, and by the same token, the primed observer would say it's x prime I hat prime plus y prime j hat prime plus z prime k hat prime. Okay. So that's all well and good, but now let's say that they're observing some moving object. So to do that, we're going to need to differentiate this with respect to time. Alright, let's just do it super carefully. So doing it super carefully, we would say this first term would actually give us two terms, an x dot I hat plus an x I hat dot, and then similarly for y and z. And then we would do exactly the same thing in the rotating system. So that will be x dot I hat, sorry, x prime dot I hat prime plus x prime I hat prime dot plus y dot y prime dot. Sorry, that should be a j there. J hat prime plus y prime j hat prime dot plus z prime k hat prime z prime dot. Let's try that again. Plus z prime dot k hat prime plus z prime k hat prime dot. Whew. Okay, now in the inertial frame, we're fortunate. The unit vectors never move, so the derivatives of them are all null vector. That's good. Unfortunately, in the rotating frame, the unit vectors are moving around, so they do indeed have a velocity. So we can kind of rewrite, so we can collapse this down a little bit. We look at this much and just say, oh, this is the velocity. That's good. And then I can pull out this term, and this term with where the unit vectors are undifferentiated. That would be the velocity measured in the rotating frame. But we're still left with three terms that we have to work with. The x prime I hat prime dot, the y prime j hat prime dot, and the z prime k hat prime dot. Okay. And so we have to think about, so we have to find the time derivatives of these unit vectors. Okay. Excuse me. Quick sidebar thought on that. Let's imagine that here's my point P, and here's my origin down here. So then this is some vector r. Okay. Let's say it's rotating around like so. Then at that moment, there we go, the velocity would be tangent. So our omega would be pointing straight up like so. Whoa, I didn't mean to do that. Alright, so our omega would be pointing straight up like that. Here, let's put in a nice little break right around there and there. That's better. Oops. There. There. So our omega points straight up like that. So we can call, whoops, purple again. So we can call this angle here phi. Well, the radius about which we are rotating, let's call that rho, that's equal to r sine phi. So we can get our v. Our v is equal to rho omega, so it'll be omega r sine phi. Now, if you go and look at the direction of v, you realize, hey, this looks like a cross product, and the only thing we have to worry about is which order do we cross r and omega. So I'll let you think about that for a second, pause the video, and then I'll get back with you. Okay, so the correct order is omega cross r. You should be able to convince yourself of that. So our velocity is equal to omega cross r, and we'll just observe that that's also r dot. All right, so sidebar completed. The reason I did that is that there is absolutely nothing special about me having used that position vector r. It could have been any vector that I wanted to look at. So the time derivative of our unit vectors will be so my I prime dot will be equal to omega cross I prime, and similarly for j and k. Excellent. So, from what we had before, we had that v equaled v prime plus these derivatives. So, v equals v prime plus an x prime omega cross I hat prime, then same with y's and z's. Alrighty, now if we think about this though, this is just a scalar. So nothing says I can't distribute that, can't associate that in to the unit vector, and that'll do the same here and here. The dot product does, the cross product does distribute over addition, so then I can pull that out. So I'll get v prime equals, v prime plus, my bad, plus an omega cross r prime. Maybe more instructively is to write it as r dot equals r prime dot plus omega cross r prime. Now, although we did this with a position vector, if you think about it, there's absolutely nothing special about our choice of vector here. It could just as easily been some arbitrary vector q. So let's go ahead and just rewrite it in general to say that the time derivative of q in the fixed frame is equal to the time derivative of q in the rotating frame plus omega cross q. So now we've got a straightforward prescription for differentiating anything where we know it better in a rotating frame. We go ahead and do the ordinary time derivative, but then we add a term of omega cross the thing. So we can extend that thought if we want to differentiate v, for instance. So v dot would be equal to v dot in the primed frame plus omega cross v, like so. Okay, so to get our acceleration then, we have to think, though, this is still omega cross v, and it'd be more convenient to get that into a v prime. So our acceleration in the translational frame will be, we're still carrying oops. Yeah, oops, sorry. This is v here. Get rid of that. In our rotating frame. Okay, so then this will equal the, oops, so we'll just write fixed and rotating there. Oh, let's just stay with the notation I just had before. That'll be a lot easier on us all. There. So my apologies, let's start over again on that. So our acceleration A will equal the time derivative in the rotating frame of v plus omega crossed with v. But we need to express those v's themselves in the primed frame. So that will be equal to, again, the time derivative in the rotating frame of v prime plus omega cross r prime plus, we'll have an omega cross v prime plus omega cross r prime. Alright, so then this first term here will become dv dt evaluated in the rotating frame plus ddt in the rotating frame of omega cross r prime. Now here we just go ahead and distribute these across. We'll have an omega cross v prime plus omega cross r prime, and the order matters, so that's the order. Okay, now this is the acceleration as measured in the rotating frame. Now to do this derivative, we've got to go and we've got to distribute it across, so this will become d omega dt in the, as evaluated in the rotating frame, crossed into r prime plus omega cross. Now notice here how I'm bringing the operator in and leaving the omega cross in front. You cannot commute your cross product. crossed into dr prime dt as evaluated in the rotating frame. Oh geez, that's awful. dt evaluating the rotating frame, plus we still have our other terms, plus omega cross v prime plus omega cross r prime. Now, if we go and take a look at that a little further, at least the one good thing we've got going for us here is with this term here, this d omega dt in the rotating frame. That could have been troublesome, but it's not as bad as it looks. And this is because if we evaluate d omega dt in the fixed frame, it'll equal d omega dt in the rotating frame plus omega cross omega, right? This is just omega crossed into whatever, but omega cross omega is the null vector, so we don't care. So that means that these two derivatives are the same, thank God. All right, so with that, we have that our A equals, so now we're up to an A prime plus, now we have an omega dot cross r prime. Now, this term here, that's v prime, so we've got two of those, plus 2 omega cross v prime plus omega cross r prime. Phew. All right, now we're not quite done yet. We still have to allow for the possibility that the system is also translating. So we need to fold in the results that we had from before, allowing for the possibility that the coordinate system is translating. So with that, we have v equals v prime plus omega cross r prime plus v naught, and A equals A prime plus omega dot cross r prime plus 2 omega cross v prime plus omega cross r. Oh, let's rewrite that. We're going to need a little more room. Okay, A prime plus omega dot cross r prime plus 2 omega cross v prime plus omega cross r prime plus A naught. Whew. All right, so that is our final result. Now, each of these terms in our acceleration has a name. So let's go ahead and name them. This guy right here usually gets called the transverse acceleration. This 2 omega cross v prime term gets called the Coriolis acceleration. It's a person's name. This omega cross r prime is called the centripetal acceleration. And then finally, that was the inertial term. Or sorry. We'll just leave that for now. All right, so let's go and look at this. Since I called this the centripetal acceleration, it would probably be good to show that this is indeed the centripetal acceleration we saw in our 200 level physics. So let's say we've got some object moving around in a circle like so. Try that again. There, it's not too bad. So omega points straight up like that. There. All right, so this is our position vector r, which is also our r prime here. That's good. And that's phi. And then once again, this distance here, this radius is rho, equals r sine phi. Okay, so now let's just go and work it out. This centripetal acceleration would be equal to rho omega squared. So it's equal to r omega squared sine phi. Alright, so now let's just go ahead and compute the magnitude of omega cross r. Well, the one thing this is guaranteed to be is perpendicular to omega itself. So this angle will be 90. So we end up with omega times this cross product here in magnitude, which is r omega sine phi. So yeah, that checks. Now we just got to get the direction. You should be convincing yourself that remember we said our velocity here was omega cross r, and if you go and do the cross product one more time, you should find it pointing into the center of the circle like that, omega cross r. So yeah, the right hand rule stuff for the cross products also checks, and you should convince yourself of that as well. Okay, in the next video we will tackle the dynamics of a particle in a rotating coordinate system.